it's about hyperbolic groups, but also it will come into play today as well. So it's not a bad thing to say any time of any day. All right. So this is so again I want to look at a word hyperbolic group. So this is a word hyperbolic group, and you'll notice a trend today is that I'm going to reserve the letter G for negatively curved or hyperbolic things, and I'm going to switch to gamma when I want to start, capital gamma, when I want to start talking about non-positively curved groups. That's really more for me than it is for you. That's for me to keep it straight. All right, so this is, I'm going to write this phrase in English, and then I'm going to tell you exactly what I mean by it. So, and I believe that Olga said this in her talk as well, is that infinite cyclic subgroups are undistorted in G. So I'm going to say it in English, and then I'm going to say exactly what I mean by that in terms of the language that we discussed yesterday. So they're undistorted in G. I believe Olga also mentioned the example of the Bohm-Slaug-Solitar group where you saw a distorted copy of an infinite cyclic group. I'm not going to worry about that right now, but that's kind of related to the last exercise on the sheet about showing those sorts of things cannot happen in a hyperbolic group. So this was mentioned in Olga's talk, but I want to say it in the language that we said yesterday. So what I mean by that is if I take a G, so a little g that generates, it's an infinite order element, and I look at the cyclic subgroup generated by that, what I want to do is I want to consider, this is one way of saying it. I could say this fancy by saying it's quasi-isometrically embedded. I could say it like that, but I want to say something more specific. So I look at the powers of G, so I consider this set. Right, and I can think about it in a Cayley graph, or if you prefer, if there's some other negatively curved space, a delta hyperbolic space on which your group acts, that's okay too, because remember, they're all quasi-isometric, so pick your favorite one, and I want to look at that set of points. So that's just a bunch of points, all right? And the idea behind this statement is that the Z subgroups are kind of lie along a line. That's really the extent of what I want to say. But I want to say it the following way. I can just think of this as a discrete set inside of whatever space I'm concerned with. Again, if you want to just think in a Cayley graph, that's probably just as easy. So consider this set inside any Cayley graph for this group. And then I want to draw a picture of them, right? They look like a discrete set. And if I want to, I can join them up with some geodesics if I want and think of it as a piecewise geodesic path as well. I could think about it that way if I don't like to look at discrete points. I can sort of join them up, right? So then I really think of this, if I join them up like that with geodesics, like that might be G and G squared and G cubed, on and on and on, and you know, G, the identity's back here and G inverse is back here, then the statement that I want to make is, the way I've drawn it here is it looks like I have a map of the whole line, the whole real line into my Cayley graph, the way I've drawn it here, where I've literally put the paths in there. And I just want that path to be a quasi-geodesic. So there exists a pair of constants, K and C, right? There exists a K, C, such that this is a quasi-geodesic, and I'll just call it a quasi-geodesic line. So it's not an actual geodesic line. And the idea here is that if we were in a nicer space, like say Euclidean space or HN, well, I can't say Euclidean space because that's not delta hyperbolic, but let's say I was working in the actual classical hyperbolic plane and I picked an infinite order isometry that's not parabolic, so it's a hyperbolic isometry, then what happens in H2 is that there's an honest to goodness geodesic line in the space on which the element acts by translation. And so I can really think of the powers as being evenly spaced along a geodesic line. And when we deltafy, if that's a verb, when we do that, we get this statement instead. That's the point I want to make, okay? And this is extremely powerful to know. It's not an easy fact to prove this either, straight from the definition of delta hyperbolic, from the definition of a word hyperbolic group. It's not straightforward to prove this, but it's true. And again, it's one of the main ingredients in lots and lots of algebraic facts about hyperbolic groups. So I was going to do one yesterday, but I ran out of time, and I'm still not going to prove this today, but I'll end up doing a proof that's a lot like it in the setting of non-positive curvature. So I'm going to say what fact I would have proven yesterday, but I'm not going to prove it. So you already know this from all the words you've heard, but you can directly prove that the centralizer of G modulo G, right, so that's just that quotient is finite, all right? Which of course implies, right, so I take a little g, it's infinite order, I look at its centralizer, and I don't get much more than the powers of g, right? So this implies, of course, that G contains no Z plus Z subgroups. Right, we sort of intuitively already know that G should not contain Z plus Z subgroups because G is supposed to be negatively curved and Z plus Z is definitely not negatively curved. So this fact should be intuitively clear if you've heard anything in the last 8 days, right? But this is the way to think about it in terms of trying to prove it, that you have, this way of thinking about it, okay? So again, I won't prove that, but I'm going to prove something just like it later on. So I wanted to finish that up. That would have been said yesterday. This is the important fact that I didn't get to say yesterday, and it allows you to do, it helps you with the last exercise on the sheet from yesterday. Okay. So now the second talk starts, right? So what I want to do today is move to non-positive curvature. So I struggled with, when I was writing this lecture, to do sort of the more general, to what should I do first, what should I do second. So I mentioned that I'm going to discuss semi-hyperbolic groups, and that is actually my goal for today, is to talk about semi-hyperbolic groups, give the definition and the motivation for it. But before I do, I want to briefly introduce Cat Zero metric spaces, because that's going to be the bulk of what I do on Thursday and Friday. All right, so I want to introduce them because that helps motivate any definition of non-positively curved group. Okay, so remember, for hyperbolic groups, so we had one of the sort of summary statements I put up yesterday was that G is hyperbolic, word hyperbolic, if and only if G acts geometrically on a delta hyperbolic space. Right, that was kind of the crux of of all the things that were discussed yesterday and even in Olga's talk. And what we'd like to do is just replace the word delta hyperbolic with the appropriate notion of non-positive curvature. That's really what that would be great if we could do that. In fact, in one of Gromov's papers on non-positively curved groups, he actually puts that as a non-definition. All right, it's in the asymptotic invariance paper, it's exactly that statement. G is non-positively curved if and only if G acts geometrically on a non-positively curved space, whatever that means, right? So this is like in air quotes, right? That should be the right way to generalize. So this is what's up for discussion, is what goes here, just like what went here for negative curvature. So let's go back and think about how we thought about negative curvature. Well, the whole point of trying to come up with a class of groups that was described this way was to think about, we already actually have lots of groups in nature that possess similar qualities, but yet they all seem to have a slightly different definition. So you try to find a unifying definition that contains all of those groups. So there's lots and lots of negatively curved groups out there, things like fundamental groups of, classical Riemannian manifolds of strict negative curvature. That's certainly a large class of very important groups that you would want to be called negatively curved, right? And then there's things like free groups, because they act on trees, and trees are pretty negatively curved. So you'd want those to be in there. And then you want some other things to be in there that are more combinatorial, as I heard you talking about. You want certain complexes that say polygonal complexes that look like they have negative curvature because you've glued lots of them together in a particular spot. And we'll talk a lot more about that in the next 2 days. So there was this theory, there's the theory of small cancellation that picks up on that says, well, I can sort of combinatorially talk about negative curvature, and I can combinatorially talk about non-positive curvature. But You want those all to be under one umbrella, and it turns out delta hyperbolicity is that umbrella that contains all of the groups that you and I can come up with that we already knew that should be negatively curved. Okay, so that's the idea. And you want to do something similar here, but it's trickier. What was so great that worked here was that this is a notion that was invariant under quasi-isometry, right? That each one of those classes that I just named was delta hyperbolic because, oh, it just naturally was delta hyperbolic for whatever reason, and then I could switch generating sets, or I could go from the group to the space. I could do all these things just using quasi-isometry, and this property didn't change, okay? This is harder, and I alluded to the reason yesterday. So the reason that this worked out so well with quasi-isometry was this stability of quasi-geodesics. Okay, that very last thing I did on the board yesterday. So for example, even here, this is a quasi-geodesic, and I said intuitively, really you should be thinking of a geodesic line with these points evenly spaced and acting by translation. Up to quasi-isometry, that doesn't really, there's no difference in our brains, okay? So the problem is you do not have that property down here. So here's the first real issue. So this is like a first real issue, and that is that, and again, I haven't even given you a definition of non-positively curved, but I'm going to certainly, whatever definition I give you, Euclidean space better be it, better be one, right? So whatever. So now again, go back to our reasoning of which kinds of things should be in this class. Well, certainly groups acting on Euclidean space should be in this class. They're definitely non-positively curved. So should compact Riemannian manifolds of regular classical non-positive curvature. Those should be in there. And again, certain combinatorial complexes that I can build that come from small cancellation theory or other places that deserve to be called non-positively curved. So whatever definitions I give you, hopefully it contains those classes. Otherwise, I've done something wrong, all right? So let me say it this way. Instead of saying in a space of non-positive curvature, I'm just going to pick one. So in just the Euclidean plane, which better be non-positively curved for whatever definition I have, in here, quasi-geodesics behave badly. All right, so what I mean by that is they don't have the stability property, right? So they do not satisfy the stability property that I put up yesterday. Okay, in fact, if you draw the logarithmic spiral in the plane, that's a quasi-geodesic, right? So if I look at this, the usual map, if I can remember it, here's one way to think about it, I guess. I guess you could do this lots of ways, but I think this is the way I think of it as a parametric curve. Right, there's lots of different ways you can write it, but this is a map just from, R into the plane. It's the logarithmic spiral, right? The one that spirals out forever and ever like that. This is a quasi-geodesic. I left that in the exercises for you to think about, or you can even look it up online. It's written down in every set of notes on geometric group theory. It's in there, so you can think about that. It's a quasi-geodesic, and it obviously does not have the stability property, right? There's not one geodesic that thing lies close to. So they're really, really badly behaved in Euclidean space. Okay, so that's a big issue. All right, so now let's go back to thinking about what a non-positively curved space should be. I've given you sort of the prototypical example. That's the Euclidean plane. And I just want to point out some properties of the Euclidean plane that you might want to model, right? So in hyperbolic space, what we wanted to do is we wanted to find a condition like this, delta hyperbolicity, that all of those spaces, all those ones I described, that they all satisfied. All right, one way to think about that is that, if I look at the universal cover of a Riemannian manifold of negative curvature, it certainly has delta hyperbolic triangles. Or if I just look at H2, I can actually figure out what the delta is, right? So I want to do the same thing here. In E2, what are the properties that E2 has that I might want to generalize? So I'm going to write down one property that's going to come in handy for one of my definitions. So here's a property of there's something that happens in Euclidean space. And in fact, it happens with triangles. So that's good because triangles worked before. Maybe triangles will work here too. So if I draw a Euclidean triangle, so that's not, it looks Euclidean. I hope that's Euclidean. And here's, so what do I mean by that? I've picked 3 points. Now in Euclidean space, there's unique geodesics between those points. So there's actually a unique geodesic triangle once I pick those 3 points. And what's true about it is this. If I go halfway out along here and halfway out along here, then what's true about that? So if I go halfway and I go halfway, what do I know about that length? Anybody? Nobody actually remembers Euclidean geometry. That's what I found out. Like, I'm still trying to learn Euclidean geometry, like, and I'm almost 50. I'm still trying to learn it. Every time I see something, I'm like, shouldn't I know that from like the 3rd grade? And then I realize I don't. Similar triangles, right? Like that geometry teacher in high school, they told you this and you have forgotten, right? So that if I go halfway out, the distance between there and there should be half of what that distance is, right? So let's put that as, let's just say P and Q, and let's call that B and C, and we'll call that A. Then the distance between P and Q, and remember, those were chosen to be the halfway points, is 1/2 the distance between the end. Don't be embarrassed about your lack of Euclidean space knowledge. Do not. Scream it out loud and say, I really want to know more, okay? So that's true. We have similar triangles. You can even say something slightly more general. You can say something about parallelograms, right? You could go like this. You can even draw it more like this. Say this is your picture, and then these are 2 different distances. Then you can say that if I go halfway out, that's equal to like 1/2 the maximum of the other 2 sides. That's like a linear algebra thing I think you proved somewhere. Again, it's a Euclidean geometry fact that you probably forgot. But it's another way to think about it. So again, it's if I go halfway out, then the distance between P and Q is half of the maximum of these 2 sides. Let's just call that D1 and D2. The sum. Thank you. That's what I meant. I'm already thinking of my other definition. See, you know Euclidean geometry better than me. Later on today, I'm going to replace that with a maximum. That's why. So again, yes. So that's, you guys remember it. That's awesome. All right. So this is an important fact about the Euclidean metric, right? It's called, one way to think about it is it's called convexity of the metric. All right. But let's just think about it in terms of pictures and not worry about the technical definition of what it means for a metric to be convex. Okay, so that's the kind of thing we want to imitate. So what I want to do first is I want to give one notion of non-positive curvature. So I want to talk about the Cat Zero Inequality. All right, so here's what it is. So let X be, and always today, I'm going to say proper geodesic metric space, even though some of my definitions don't require it. I'm just going to always have it in there so I don't say anything wrong. All right, so this is a proper geodesic metric space. Then X satisfies the Cat Zero Inequality if. All right, so here's a big if. So there's some quantifiers. So first I'll draw the picture and then I'll write it in words. Here's the picture, is that if I take a geodesic triangle in X, I don't want it to look like a delta thin triangle. It's hard not to draw them like delta thin triangles. So there's A, B, C. This is happening in X. So that means I've chosen 3 points and 3 geodesics. Now, in Euclidean space, they're unique, but they don't have to be unique here. It's just a choice of, so that's triangle ABC. All right. And what I'm going to do is I'm going to go over to Euclidean space, and I'm going to pick a triangle that has the same side length, an honest to goodness Euclidean triangle. So I'm going to put bars over here, over these things to let you know I've moved over to Euclidean space. So this triangle has the same side lengths as this one. Okay? That's called a comparison triangle. And then the Cat Zero Inequality says that anytime I have one of these, I compare it to its counterpart over in Euclidean space, and then what I'm going to write down is an inequality that tells me this one is no fatter than this one. It's not any fatter than this one. Okay? So what it's going to be is that if I pick any pair of points, say a P here and a Q here, so no bar, the distance between any pair of points on two sides, and then I go over here and I draw the corresponding points over here, that they're going to be smaller. They're going to be closer. Okay? So they're no fatter. They can be flat, but they can't be fatter than flat. That's the idea. So that's the Cat Zero Inequality. Now, the difference between this and what we looked at with delta hyperbolicity, remember, for delta hyperbolicity, we had this delta running around. Delta could be like 9 billion, right? So delta was just a constant. And in that setting, a triangle that lives in a ball of diameter less than delta could be as crazy as you wanted it to be, right? There's no restriction on triangles that live in a ball of size delta in a delta hyperbolic space. Here, that's not the case. Here, this can be teeny, teeny, tiny, or it can be gigantically large. So this is true for all triangles in the space, no matter how big or how small. There's no delta running around, right? You're really comparing all of your triangles to those in Euclidean space. All right, and there's some basic properties that are, so for example, you should be able to see right off the bat that this is really going to be a problem if I say, oh, a group is going to be Cat Zero if its K-graph is Cat Zero. Does anybody see why that's going to be true? Maybe after I write down these properties, you'll see it. Let me write down these properties. One of them is that X has, if it has the Cat Zero inequality, then X has unique geodesics. Okay?
Can you explain why it's called the Cat Zero inequality?
Yeah, so Cat Zero, well, at least the way I always learned it, is it stands for people's, there's 3 names associated to it. So it's,
to do with categories.
no, nothing or cats, actually. So it has to do with, so I probably other people have heard it, so I think of it as 3 names, Kartan, Alexandrov, Topoganov, whose name I always say wrong. But some people I've also heard say it's the comparison, so Alexandrov, I think, sort of looked at this comparison idea. That's why his name is in there. I've heard other people say comparison something something, but I think of the 3 names.
Okay,
Nothing.
Very helpful.
Yes, yes. It's like what was the name? So acylindrical was the word yesterday that we didn't know why it meant acylindrical, right? So you have to ask the person that names them. But anyway, so there you have it. So it's for those 3 names. All right, so X has unique geodesics. This is pretty straightforward to see once you think about what the Cat Zero inequality means. It really means if I had 2 geodesics like this between a pair of points, well, then if they differed somewhere, I'd be able to look at this triangle. And I would see that, oh no, they're you know, first of all, you can think about it this way. If I'm Cat Zero, then I look like the Euclidean plane. I have similar triangles. I have that same inequality on the top with a less than sign. Right? That's it. So if I'm Cat Zero, take that top picture, I have a less than or equal to sign. Right? So over here, you can see I can't have 2 geodesics between a pair of points. Because if I go halfway out, they have to be half of the distance between the other pair, but that's 0. Right? That's another way to think about it. This follows directly from that. So this can't happen. And then that implies right off the bat that X is contractible. So you get this topological property for these spaces. Right? And what you can think about is how would I show it's contractible? I can pick a base point in the space. In fact, I can draw a homotopy to a point. I can just pick any base point in the space. Right? And my homotopy is going to go like this. Take another point in the space, draw the unique geodesic back to that point, and just contract along those unique geodesics. So that's pretty straightforward. Once I have this, this is pretty straightforward. All right, so this is pretty strong. Again, much, much stronger than delta hyperbolicity. All right, so now, can you see why I can't define a group to be cat zero if its Cayley graph is cat zero? Not good. Which Cayley graphs are contractible? Trees. Yeah. Can't be doing all of them that way. Right? So not good. Not good. Not, well, it's not bad. It's just that it does, you know, if I want to put if I want to replace NPC with cat zero, that's a perfectly fine thing to do. It's just not going to be a condition I can check in the Cayley graph. All right? And that's actually one of my definitions is exactly what I just said. I'm just going to replace NPC with cat zero in that definition. So that's going to be my definition of a cat zero group. A group gamma is cat zero if gamma acts geometrically on a cat zero space. Okay? Okay, like I said, this is like one thing that kind of makes me sad is that I can't check this in a Cayley graph. Kind of makes me sad, but not that sad, as we'll see that actually I have spent most of my adult life studying cat zero spaces and cat zero groups. So I'm not that sad. But I'm only sad after watching Olga's lectures about how useful it was to think about delta hyperbolic groups that way. Yes, question?
Yeah, so what's the zero in cat zero?
Oh, that's good. Good question. So I should have said that, actually. That's a really good point. So you can actually put any real number you want there, okay? And then what you do is, instead of comparing, so you should think of E2 as the surface of constant curvature 0. That's where the 0 comes from. So I can look at a surface of constant curvature kappa and compare my triangles with triangles in that surface. So if I put a -1 there, then I'm comparing with triangles in the hyperbolic plane. If I put a +1 there, which is what I think you just said a minute ago, if I put a +1, then I'm comparing with spherical geometry. And then I have to be a little bit careful with spherical geometry because I actually can only consider triangles that live in a diameter pi set, right? I can't consider just any triangle on the sphere because I have to worry a little bit about great circles and things like that. So there's a little bit of an issue when you try to put a positive number there, okay? Remember, I'm not being positive all week. I'm being negative and non-positive, right? So, but that's a very good question. There's actually a whole theory of comparison, of comparing your triangles to those in a space of your favorite curvature, right? I meant to say that when you asked your question and I forgot. All right. Okay, so let me say, I want to switch to, again, to semi-hyperbolic, but before I do, I'll just say some other examples, some examples of cat, this is going to be like the next 2 days, we're going to be talking about cat zero groups, okay? But just let me give you some examples, and then we're going to see what semi-hyperbolic means. So the examples are obvious ones, like Euclidean space, right? Certainly, any Euclidean space is going to be cat zero, because that's where I got it from. But also, hyperbolic space will also be cat zero. So cat -1 things are cat zero as well, right? Triangles are uniformly delta thin, no matter how big or small they are. So in hyperbolic space, even the teeny, teeny, tiny triangles are not a problem. Trees, so locally finite trees. So notice I'm saying locally finite because I put proper over there. I want to just stay in the setting of proper geodesic metric spaces. So locally finite metric trees. And of course, universal covers of Riemannian manifolds. I'm not even going to write that down. Those are obviously should be, so I'll just say classical non-positively curved manifold universal covers. And I'll say Euclidean buildings, if you know what those are. If you don't, no big deal. Again, it's just what my point is that There's lots of them, okay, and lots of them that occur naturally. So these are more combinatorial objects, the Euclidean buildings. You can think of them as combinatorial objects. And also lots of two-dimensional simplicial or actually polygonal complexes coming from, I'll just say it this way, combinatorial group theory. And I'll talk more about that in the next 2 days. And of course, here's a big thing, is that direct products of these. That's important, is that this notion of non-positive curvature is closed under taking direct products. Take any two in this list, take their metric direct product, right, where you just take the metric product of two metric spaces, is just do the usual Pythagorean way of defining a metric on a product, you will get another Cat Zero space. Okay, that's important because that gives you lots and lots of kind of what I like to think of as mixed examples. And also, you can do other constructions where you glue. So there's gluing constructions. So gluing constructions that preserve Cat Zero. So it's pretty filled with cool examples. Okay. And then once you take my definition, then once I tell you the examples of these spaces, you automatically get examples of groups, right? Because when I think about groups that act geometrically on Euclidean space, I get things like the free abelian group of rank n, right? And here I can just get any group that's acting properly and co-compactly on Hn, so that's lots of all hyperbolic, compact hyperbolic manifold groups. Free groups, finitely generated free groups, lots and lots of really cool lattices inside of important algebraic groups, other cool groups that come from combinatorial group theory, and then direct products of these groups. So I can switch from the spaces to the groups once I understand the groups that can act geometrically on the spaces. All right? So that's going to be the major viewpoint that I take in the next 2 days, is I'm going to be looking at that class of groups. But before I do, I want to sort of tell you a little bit about the history, and in doing so, I want to introduce semi-hyperbolic groups. So there are other candidates for classes of non-positively curved groups. Like I said, this is just one of them. In fact, there's lots of them out there. The way that you can think about it is I want to take some feature of Euclidean space and I want to try to define a class of groups around that feature. That's right, that's the whole idea of delta hyperbolicity. So I just gave you one candidate. Another candidate that you could do is you could say, okay, and I know Olga mentioned this in her talk, here's another feature of Euclidean space that you might want to generalize, and that is that you know that if I take a loop of size n, look at that, I didn't even draw it dotted, and it's still pretty good, right? So if I take a loop, I just can't even help it anymore. They're perfect every single time. If I take a loop of length n, it should enclose an area of about n squared, right? So I know that Olga gave some examples in there. Encloses an area of about n squared, up to some constant multiple. That might be another thing you want to say, okay, I'm going to use that as my way of capturing some class of groups. And if you do that with groups, you could come up with, so if I want to pass now to the world of groups, those are groups that satisfy, a quadratic isoparametric inequality. Right? So when you're trying to figure out something to get your handle on in a big huge math problem like this is the kind of thinking that you do like in private, that you don't even tell people you're doing. You just like sit there and you do it and you hope that nobody's watching you, and then once you get it all nailed down, then you go give a talk on it and everybody thinks you're awesome. But like this might be something you would sit and do in your living room and say, all right, That's a cool feature of Euclidean space. That's what it turns into when I think about groups that have that property. And you say, okay, well, maybe that should be my class of non-positively curved groups. Maybe just groups that satisfy a quadratic isoparametric inequality. All right, and then you can argue with people because maybe their class is better than your class. So it turns out all the proposed classes of non-positively curved groups that have been put out there over the last 20 years satisfy this. So that's sort of one of the checking points. So I'm going to give you two classes of non-positively curved groups today, and both of them satisfy that property. There are other ones. There are weaker and weaker properties that you could put that will imply quadratic isoparametric inequality. So I think we can all agree that that's something that should be common to all of them as well, because this is a pretty important feature of Euclidean space. All right, so again, that might be a class. You might want to say, oh, I'm just going to call groups non-positively curved if they satisfy a quadratic isoparametric inequality. And there wouldn't be anything wrong with that, really. That's certainly an okay thing to do.
Do you have a favorite class?
Yes, well, the Cat Zero ones are my favorite class, but I really also like this class. I like to think about the groups that have quadratic isoparametric inequality that aren't in any of the known geometric ones. Right, so this is a condition that doesn't have anything to do with me acting on a space geometrically other than my Cayley graph. So I'm not borrowing the geometry from somewhere nicer. I'm just looking at its Cayley graph, looking at a loop, and counting how many relators I need to fill a loop. Right, it's something like at the other extreme. I'm totally looking at the combinatorial group theory and not at all borrowing the geometry from differential geometry or anywhere else. Yes?
So what's an example of a group that's quadratic isoparametric inequality that's like not Cat Zero or like Hyperbolic?
So you can look at lots and lots of extensions of Fries by Z. So all of these are have quadratic isoparametric inequality, but many of them are not Cat Zero because they fail some other condition. In fact, let me see if I can write one down. I believe I can write one down. I think I can do one like this. Gersten's example, I can write one down. So that's where I'd have to write down a matrix, which means I'd have to remember something, which is never good if I have to remember the matrix. So I can write down a group that looks like this, that has, it definitely has quadratic isoparametric inequality, because all of these do. That's a huge theorem of Bryden and Groves, that all of those extensions do. But you can come up with one that's going to violate the property of Cat Zero. It's going to violate the flat torus theorem. So that's one of my examples. I just haven't written down the matrix in the last 24 hours, so I don't remember it. But that's a good example to think about. All right. I also guess things like I think, no, that doesn't have quadratic isoparametric in it. Well, these are good ones. These are pretty straightforward. Like I'll give you an easy one particular one tomorrow, I promise. Promising Kasha specifically that she's getting her example. Yes?
So the idea is you want to look like Euclidean space, but in more general.
Yes, that's right. You want to look at some sort of asymptotic property that approximates that. Sometimes it can be an asymptotic property. This one's more of a local property, right? This says, I want all triangles. This is more of a local thing. Triangles that big and small actually have to behave like Euclidean triangles, right? This one's more of a large scale one. This is a large scale one, right? This is, okay. All right, good question though about that, and I'll do some more of those. I felt like there was a better one on the top of my head that you would recognize, but this is certainly going to be one. Now I'm going to be distracted by that because I won't remember the matrix, but that's okay. I'll get it. It'll be the first thing I do tomorrow. All right. All right, so now let's talk about another attempt. Another attempt. Okay. So this is going to be the semi-hyperbolic groups. And this is going to be more along the lines of thinking about the large-scale change of those convexity properties. Okay? So I have to start with a couple definitions. This looks a little bit technical, but don't fear, it's not that bad. All right? It looks a little bit technical, but you have to you have to just say a few things. So what I want to start out with is, again, I want to start out with X. And most of the time, I'm proper and geodesic. But really, for this definition, this first thing I'm going to write down, I can do this in any metric space. OK? So I want to consider. First, let me say what the idea is before I give the technical definition, because I hate writing down a technical definition. Everybody's busy copying it, and then they don't hear the really, really cool thing that I say about what it really is. So the idea is that I want to borrow the geometry from some really nice space, but only in kind of a discrete large-scale way, rather than in a really, really cool, like that comparison way. I want to do a different kind of way of carrying my Euclidean geometry or non-positively curved geometry to something more discrete like a calligraph of a group, okay? And so what I'm going to do, I want to use the same kind of formula that I did before, which is, okay, well, what is it about negative curvature that's important? Well, thin triangle, so I need to define what it means for metric spaces to satisfy this, and then I say that a group satisfies it if a calligraph satisfies it, or if it acts geometrically on it. That was the way I did it before, and I kind of want to do that same thing. The problem is the quasi-geodesics don't behave well for non-positive curvature, as we said. So what I'm going to do is, if I had a really nice space, and I map it to my, say my group acts geometrically on the space, so that I have this quasi-isometry between x and gamma, or gamma and x, whichever direction you want to think about it in, because remember, if I have it in one direction, I have it in the other. So I'm going to stand in X, and I'm going to say, oh, my geodesics are beautiful, they're awesome here. I'm going to map them over to my calligraph, and all I get over there are quasi-geodesics. And I could get, you know, between any pair of points in my calligraph, I can have lots and lots of quasi-geodesics, and they don't behave well. So what I'm going to do is I'm going to make a choice. I'm going to have to make a choice of a quasi-geodesic. So that's what this definition is about right here. So what I want to do is I want to consider some discrete paths. These are, so P is eventually constant. So I'll say what I mean by this in just a second. So what do I mean? Well, by eventually constant, I mean that, I mean eventually constant. And we're going to let TP equal the largest integer for which, you know, right? It's kind of technical, but all I'm really saying is that I'm mapping just the naturals in, and at some point I'm going to stop, right? I'm going to get like kind of a finite discrete path between any pair of points. That's what I want to get eventually. Not equal to, I do, yes, thank you. Thank you. Right? And so now I want to give this definition. So a discrete bicombing of X is simply a choice. So it's a map. It's a map like this that sends each pair. And so S of a pair, I'm going to denote it like this. It's just a discrete path between X and Y. It's not really a path, it's just a discrete set of points between X and Y. Between doesn't really even make sense. And all I've just done is just chosen some points. There's X and Y, and then I've chosen some points. That's all I've done, right? Okay, this is called the combing line between X and Y. And it, again, line is deceiving, and so is the word between. Yes?
I have a question about the TP definition.
Yep.
So it's P, is that
Oh,
minus
sorry.
1 of the subscript?
No, it should not be. It's one of those tech errors. I just did a LaTeX error, live and in person. Right, I put my bracket in the wrong place. Oh no, I go to compile, no error, yet everybody knows it's wrong. All right, good. Thank you. You can forever be my tech editor. All right. Okay. So now I want to put a couple properties onto that, because that's not enough to do anything at all. Oh, and one thing I want to say is, so I've done this as if it's discrete, but notice if X were a geodesic metric space, if it really is a geodesic metric space, then once I choose those, I could just draw little geodesics between the points and really think of it as a piecewise geodesic path. And that's really what we're going to be doing in a Cayley graph or anywhere else that we're going to be working. But the definition doesn't require me to use that. But I'm just saying that's why I keep using the words line, path, because I'm really thinking in that context of picking some discrete points, drawing geodesics between them, and getting some sort of weird path between x and y. That's what I'm thinking of, okay? It's just that that weird path has to go through these certain points that have been picked for me already. All right, and then a bicombing, so here's some properties. So a bicombing is called quasi-geodesic if there exist constants such that all of the combing lines are quasi-geodesics, right? So again, remember, quasi-geodesic just has something to do with distances. I don't really need to see a path there. I just have to know the distances between the pairs of, between the points that are in this discrete path, okay? And then the last property is the one that's going to model that stuff over there, okay? And so a bicombing is called bounded if there exists some other constant c. So, oh, I can't use c. Ruh-roh. I can't use c. I better use d. Oh no, you can't be using capital C twice. That's not good. I just noticed that. Oh, actually, no. I want to do it this way first. If there exists constants, I'm going to do this one first. Constants k1 greater than or equal to 1, and little k2, no, these are little k's, not big k's, greater than 0, such that the following picture holds. All right, here's the picture. So I need 4 points now because I want to model that convexity thing. Here's what I'm going to get. I have this funny combing line from x to y. It's quasi-geodesic though, and I have another combing line from x prime to y prime, right? And they don't have to look, it looks like these two are the same distance apart, but I don't mean for that to look that way. I don't mean for this to look like a parallelogram. Let me put it down there like that. So I have that combing line and that combing line, right? And then what I need, I'm just going to call this distance, so there's my x, this is just d1. It's just easier to write it than it is to keep writing the distance function. That d, let me call it d1 and d2, I guess. So that the distance, I'm going to draw this picture. So this is a combing line. So the distance between, if I look on the top combing line at time t, and I look at the bottom combing line at time t, that's less than or equal to, now you're going to see where I messed up that max before, k1 times the max of the end distances plus k2. Okay? So this distance, I go same less than or equal to this number. So it's meant to model that second picture I have over there. All right?
I have a question, because you're not asking that the distance between the lengths of the combing lines are the same.
Nope.
So if you go out the same distance, I mean, one of them might be hugely longer
That's
than the
right.
other. So you've gone out, say, distance 5 on each of them.
Yep.
And that's still meant to work.
Yes, that's still meant to work. I know it sounds crazy, right? Remember, but one of them's eventually constant. If they're really shorter, then one of them's eventually constant. So yes, you're comparing it with that. Yep,
yeah,
for all
that
t.
makes sense. Okay.
Yep, so it has to be for all t in n.
Okay.
Is this somewhat like a fellow traveling property?
Yes, it is. Nice. In fact, biautomatic groups are this, whatever I'm calling this. Yes. In fact, I'll put up another equivalent condition in a minute that'll make you like it even better. Oh, T is, remember, these are maps. So remember, these guys are maps. That's why I'm really marching. Think of them as marching out integer times, right? I've drawn them again, and I've drawn them like they're paths. They're really discrete paths, right? But I'm thinking in a geodesic space, so I can just connect them all up with dots. So that's why I've drawn it like it's a path. But I'm really only looking at the integer points. This only has to be satisfied for the integer points on that. That's another point, right? Point, point, point. I keep saying the word point, but that's why I gave that definition about, right? Like this could be the connecting of the dots can be confusing, but it shouldn't be confusing, right? All right, so soak it in because it's kind of technical and it looks not helpful yet, right? It kind of looks not helpful yet, but I'm going to give a definition. So we say, you'll see why I'm doing it this way. First of all, we'll say that x is, and I'm going to put this word in there. I can't remember whether you're supposed to hyphenate semi-hyperbolic or not. Sometimes I do, sometimes I don't. If x has one of these bicombings, so if x has a quasi-geodesic, a bounded quasi-geodesic bicombing. All right. Now, that looks technical, but what's really cool about it is this is something that can be checked in a Cayley graph. This is great. So in the Cayley graph, now think instead of just a generic metric space, think about a Cayley graph. What I can do now, this choice really means, so I can choose quasi-geodesics between pairs in the Cayley graph, and I can try to get this geometry satisfied. All right, this is something I can check in a Cayley graph. So in fact, a group is semi-hyperbolic, or in fact weakly semi-hyperbolic. A group. In fact, I'm going to say finitely generated is weakly semi-hyperbolic if any, so if A, which is going to mean any, Cayley graph is metrically semi-hyperbolic in that sense. Okay? So that's a perfectly fine definition. It's invariant under quasi-isometry. Quasi-geodesics go to quasi-geodesics under quasi-isometry, right? So that's good. And this bounded property, anything that has the word bounded in front of it is going to be invariant under a quasi-isometry, right? So all of these constants get changed in some linear way under quasi-isometry. So that's cool. That's the important feature of this definition that we didn't have with Cat Zero. It's not invariant under quasi-isometry. If I take a quasi-isometry of a Cat Zero space, I am not going to get a Cat Zero space. So that's not there, but it is here, okay? So this is invariant. It's easy to see right off the bat that it's and well, let me say it this way. It's invariant under quasi-isometry. And now you should wonder why I'm putting the word, I'm not typing, I'm writing with chalk. Why I'm putting the word weakly in front of it. Because here's what happens. So here's the story. There's always a good story. So first of all, this definition can actually already get you a lot about these groups. So this is, again, it's really just an attempt at trying to take something from Euclidean space and doing the right thing, making it some large-scale property that's invariant under quasi-isometry. So we did that. And it turns out just this class of groups, which are called weakly semi-hyperbolic, you can already prove they're finitely presented. So if I'm one of these, then I'm finitely presented. And I have a quadratic isoparametric inequality. So that's pretty good. That was sort of one of my checks, right, that I said I wanted to be there if it was going to be non-positively curved. So that's good. all right? And also, it generalizes hyperbolicity because it's really, really easy to check that, in fact, I left this as one of my exercises, is that a delta hyperbolic metric space is semi-hyperbolic. All right, so that's another cool thing. So let me just say that. So this generalizes, so hyperbolics, delta hyperbolic metric spaces, or I can put the word group here, are semi-hyperbolic. And the way that I have to actually prove that is the following. I'll just outline the proof of that, is that you actually have to show that what you show is that if I have to pick a bicombing, right? So what I can do is given any pair of points, I can just pick any geodesic between them, right? Remember, think about the Cayley graph of a word hyperbolic group. Just pick any. Choose a geodesic. So choose S, X, Y to be any geodesic, which is clearly a quasi-geodesic, right? And then when I go to check the bounded property, then I can just use the fact that thin triangles implies thin parallelograms, essentially, or thin quadrilaterals. That's the extent of what so the extent of proving this is to show that you can get that picture to work out. And it's pretty straightforward once you have thin triangles, right? You're going to have to, your constant here, these K1 and K2s are going to depend on delta. All right. So that's good. It's a generalization of a class that we wanted to generalize. Yep.
What is the intuition behind the fact that this property is actually preserved under quasi-isometry,
Yep.
not the other one, not
The Cat Zero one? So think about it this way. So let's look at the Cat Zero property. If I have a Cat Zero space and I have a group that acts geometrically on it, right? Like think about Z2 and R2. This space is Cat Zero. This group is quasi-isometric to this space, but this group is not as a metric space. Its Cayley graph is not a Cat Zero space. Its Cayley graph is the integer lattice. That's not contractible. Right? So it's totally not meant to be preserved under quasi-isometry. Right? Does that make sense?
Yeah, it's just the other one.
Yeah. So here, what you're doing now, remember, now you'd be making a choice. You'd be making a choice of one geodesic. So think about R2 is semi-hyperbolic, right? R2 is semi-hyperbolic because I can just take any pair of points and draw its regular old geodesic between it. And because it satisfies that property, it satisfies this crazy weaker property. So this guy is the Euclidean plane is semi-hyperbolic. For Z2, that's quasi-isometric to it, it should be semi-hyperbolic. Semi-hyperbolic. But that means that I will have to pick a quasi-geodesic bicombing of the group. So I don't consider the whole entire picture, right? I have the whole integer lattice, but for any pair of points, I'm going to be picking a geodesic. I might as well pick a geodesic instead of a quasi-geodesic. Maybe for any pair of points, I'm always going to do the over-up. That might be the way I make my choice. Okay? And if I do that, then that structure is semi-hyperbolic in the sense that I've just defined. Okay? That's a good question, though. I've set this up to be quasi-isometric invariant. That's the point, is I really made it that way because I already understood why Cat Zero wasn't. Right? Does that make sense?
Yeah, I just wanted to know how you made this up in order to be like,
Yeah, well, I didn't make it up, actually. I should have said that. This is a definition due to Bridson and Alonso. I should not be taking credit for stuff other people do, but thank you for trying to give it to me. But it's, but this was a class of groups introduced by Bridson and Alonso a long time ago now. But anyway, that their thinking was, I want something quasi-isometrically invariant, because they went to lots of conferences and everybody else was trying to do it too. All right. And again, so my time's almost up, but I want to say that it includes all the classes we want it to include, actually, or at least the ones I want it to include. That is, it includes the Cat Zero ones. We'll see that Cat Zero groups, all Cat Zero ones are going to be semi-hyperbolic. And of course, I'm going to have to tell you what happens when I erase the word weakly. So this already is pretty strong, But it turns out if I put one more extra thing on there that has to do with equivariance, that I get a much, much richer class of groups. I get really nice subgroup structure. I can prove a lot more if I put just one little extra thing that already should be holding anyway. So I'll convince you of that tomorrow. And it includes, like I said, Cat Zero groups. It includes biautomatic groups, which come naturally with a bicombing from the biautomatic structure that has the fellow traveler property. And the fellow traveler property is, in fact, you can restate this condition in terms of a fellow traveler property, which I'll do as well. All right, so it's a really broad class, and that contains lots of our favorite classes that we like to study. That's the kind of point. So tomorrow I will get rid of the word weakly, and then I will talk about why some of those other classes are semi-hyperbolic. All right? I don't want to go over. Oh, yes. This one, so the Gersten example will not be. Wait a minute. It might be. I have to think about that, whether that's semi-hyperbolic. Because the reason it's not Cat Zero is because it violates the flat torus theorem. There is a flat torus theorem. Actually, it might not be, because there is a flat torus theorem for semi-hyperbolic groups. I'm just not quite sure if it's strong enough to rule this out, but I think it is. I think I can rule that out. Ilya, you might know.
Sorry, I came in late. I don't know what fit there is.
Well, that's because you missed the matrix. Oh, well. No, it's the Gersten example where he shows it's not Cat Zero by getting a bad plane in there. Don't worry, we're not putting you on the spot, Ilya. Well, I kind of did, but now I'll take the spot off of you. I'm pretty sure that we can prove this one is not semi-hyperbolic. All right, thank you.